We are now ready to continue. We're ready for problem 19. So let me open up the test. All right, problem 19. Find the exact value of sine 2 theta, cosine 2 theta, and tangent 2 theta for the given value of theta. So problem 19. The information we've been given is cosine of theta equals 4/5. And they tell us that the angle theta is between 0 and 90 degrees, which basically means it's in quadrant 1. And of course, more than ever, I'm going to be using my formula sheet. Let's switch back. So here I've got my formula sheet. Here I've got the double angle formulas, which this question is about. So first we'll look at sine of 2 theta. The formula of sine of 2 theta is 2 sine theta times cosine theta. So I need to plug in sine theta, cosine theta. I've already got cosine theta. If I can determine sine theta, then I can solve this problem. What I'm going to do, what I like to always do, I take the information I'm given, and based upon this trig function, I create a right triangle. And once I know all the sides of a right triangle, then I can determine all the trig functions. So I'm given cosine theta is 4/5 cosine, so ca is adjacent over hypotenuse. The remaining leg of the triangle is going to be the square root of 5 squared minus 4 squared. It's 25 minus 16 squared, or 9, which is 3. So it's a 3, 4, 5 triangle. So now I'm ready to, and since this is quadrant 1, I know all the trig functions are going to be positive number. 2 times sine of theta. Sine is so, opposite over hypotenuse, times the cosine of theta, which I can either look here, or I was already given the cosine of theta, either one. Multiply these fractions, times 2, so 12 times 2 is 24. Looks like 24 over 25. Next, they want to know cosine of 2 theta. Now, cosine of 2 theta is interesting because when you look at the formula sheet, there are 3 choices. And doesn't really, you can do whatever one you want. I guess, I don't know. Just for fun, maybe I'll choose the middle one. Or I can choose, since they gave us cosine of theta, maybe I'll choose the last one. You're going to get the same answer no matter which one you use. Maybe I'll use this one, 2 cosine squared of theta minus 1. Cosine theta is 4/5, so 4/5 squared minus 1. When you square a fraction, you square both the top and the bottom. So 2 times 16 over 25 minus 1. 32 over 25 minus 1. I need to turn the 1 into a fraction with a denominator of 25. So after you do all this math, looks like 7 over 25. Then finally, tangent of 2 theta. The formula is 2 tangent of theta over 1 minus tangent squared of theta. So it looks like this formula just involves the tangent of theta, but I can get the tangent for my right triangle. Tangent is TOA, opposite over adjacent. Looks like tangent's 3/4. So 2 times 3/4 over 1 minus 3/4 squared. 2 times 3/4 is 6/4. 1 minus 3/4 squared is 9/16. So now I've got some math to do. Let's first look at the denominator and combine 1 minus 9/16. 1 is 16 over 16. Actually, I can reduce 3/4 to 3/2. So 16 over 16 minus 9 over 16, 17 over 16. And now, complex fraction, take the top fraction, multiply it by the reciprocal of the bottom fraction. It's like 48 over 14, which reduces down to 24 over 7. Now I'm going to go back and look at the answer. And hopefully, we'll have the correct answer. I'll go turn on the key and then jump back to problem 19. So the sine of 2 theta 24 25, that's correct. Cosine 2 theta 7 25, and 100%. Looks like it's correct. All right, that's good. So now on to problem 20. Same kind of problem. Sine 2 theta, cosine 2 theta, and tan 2 theta. Let's write down the information we're given for this problem. Cotangent of theta equals 3/4. And now they say for this problem, theta is greater than 180 degrees, but less than 270 degrees. Where is that at? That's actually the third quadrant. So as I begin to use trig functions, I have to keep in mind theta is in the third quadrant. Let's go ahead. I know all these formulas involve sines and cosines and tangent of theta, so I need to have a way to determine those. Let's go ahead and take the information I'm given, and I'm going to eventually create a right triangle so I can figure out all my trig functions. Well, I don't like to normally work with cotangent, but I know if I take the reciprocal of the cotangent, that's actually the tangent. So now that I know the tangent, I can go create a right triangle with the angle theta. TOA, right? Tangent is TOA, opposite over adjacent. And if you use Pythagorean formula, I already know this is going to be hypotenuse of 5, so it's another 3, 4, 5 triangle. I got to remember this angle's in quadrant 3. So now, use the same formula as 2 sine theta times cosine theta. Sine of theta, sine is opposite over hypotenuse, but it's in quadrant 3. So it's actually -4/5. Cosine theta, so ca adjacent over hypotenuse 3/5, but it's in the third quadrant, so the cosine is actually -3/5. So the two negatives make a positive. 12 looks like sine of 2 theta. Sorry. Keep forgetting that. Sorry. You heard me say it, now you can see it. here's the information we're given. I know this angle's in quadrant 3. I changed cosangent to tangent. With the tangent, I created a right triangle. So now I went to do sine of 2 theta. Here's the formula. Plug in the sine of the cosine. There you go. For cosine, just for fun this time, let's use that first formula. Cosine squared theta minus sine squared theta. I've already figured out cosine and sine from up here. Cosine was like negative 3/5, so negative 3/5 squared minus negative 4/5 squared. It's 9 over 25 minus 16 over 25. If I didn't make any math errors, hopefully that's the cosine. Then the tangent of 2 theta, the formula is 2 times tangent of theta over 1 minus tangent squared of theta. Tangent is TOA. Actually, I can look at the triangle, I can look up here. I already know what tangent of theta is. 4/3, 1 minus 4/3 squared. So this is 8/3 over 1 minus 16 over 9. 8/3. 1 becomes 9 over 9. So minus 7 over 9. So then simplify the complex fraction times negative 9/7. Actually, these can cancel. Once again, I didn't make any math errors. Those are my answers. So let's go back and see how I did. This is number 20. Go turn on the key. Sine 2 theta, 24, 25, that looks correct. Cosine 2 theta, etc., 25. And tangent, yep, looks like those are all correct. So that's good. All right, let's go to 21. I gotta remember to share the screen once I start the problem. So if tangent of alpha equals 7 and alpha is acute, then find the sine of 2 alpha. So it's really almost the same kind of problem, although it's simpler, because they're not asking for all 3 of the trig functions. They're just asking for the sine. So basically, tangent of alpha is 7. Alpha is acute. That means the angle's in quadrant 1, and they want to know the sine of 2 alpha. All right. Well, the formula for sine 2 alpha is 2 sine alpha times cosine alpha. So I'm going to do what I've always done. I will take this trig function and create a right triangle. Once another right triangle, then I can figure out sine and cosine and plug them in. So these last 3 problems have been pretty much the same. Tangent of alpha is 7, although tangent is TOA, opposite over adjacent. So I want this to be a fraction, but the way I turn it into a fraction is just make it 7 over 1, right? So opposite over adjacent. What's hypotenuse going to be according to the Pythagorean formula? 7 squared plus 1 squared, 49 plus 1 is 50. But 50 can be broken up to 25 times 2, so it looks like 5 square root of 2 for the hypotenuse. So therefore, 2 times the sine of alpha. Sine is opposite over hypotenuse. Cosine of alpha, so ca, adjacent over hypotenuse. And now if I multiply this out, I get 14. 5 times 5 is 25. Square root of 2 times square root of 2 is 2. It's like 14 over 50. Which reduces down to 7 over 25. And like I said, that's all they asked for on this one part. So let's see if I did it correctly. Number 21. Turn on the answer key. Oops, that's already on. Number 25. All right, that's good. So far, so good. All right, let's see if we can get through these. How about moving on to 22? Another one of these. Wow. All right. We should be getting pretty good at these by now. You write down the information we're given. Secant of theta equals 5/4. The angle theta is between 0 and 90 degrees, which is quadrant 1. Oh, I'm sorry, this is different. Now they're asking for the half angles. Sine, cosine, tangent. All right. So let's talk about half angle formulas. Once again, it's interesting, if you go to your formula sheet, look at these half angle formulas. Let's talk about this. First of all, they're all 3 square roots. And look what's inside the formula. All of them only have the cosine. So as soon as you know the cosine, then we can basically calculate the half angles. But what's also interesting is look here, it's plus or minus all 3 of these equations. Now for each of these problems we solve, there are not going to be 2 answers. There are not going to be a plus and a minus answer. There's only one answer. So as we do these problems, we have to figure out for each of these, should the sign, should it be a plus or a minus for each of these? So let's talk about how to do that. So the point I want you to see is that we have to we're really working with 2 different angles here. We're first of all dealing with our original angle theta, but then we're also dealing with theta over 2. Because the original problem was given to us in terms of theta, but then we're asked, so this is sort of this is information we're given, and then this is what the question is about. So here's the deal. When we're trying to solve these problems, we're going to be using information about theta, because you look at all those equations. So for instance, let's just write down, probably easiest if I start out this problem and explain what we're going to do. Here's the formula for sine of theta over 2. It's plus or minus the square root 1 minus cosine of theta over 2. So here's what I'm trying to figure out. Sine of theta over 2. My formula says, you know what? All I need to know is what the cosine of theta is. If I know the cosine of theta, I can plug it in. Although there's some unknowns there, because I can plug it in and I can figure out what the square root is, but then I've also got this plus or minus. So, and it's not going to be both. It's going to be one or the other. All right. Say that from the top. It's one or the other. It's not both. So which one is it going to be? So two things are going on. When I do the actual calculation, I'm going to plug in for cosine of theta. And when I do that, I need to know if cosine of theta is a positive or negative number. And that's going to be determined by where is the angle theta. They told me theta is in the first quadrant, between 0 and 9 degrees. So I have to keep that in mind when I get ready to plug in cosine of theta. Obviously, cosine of theta in the first quadrant is a positive number. So when I plug in cosine of theta, I'm going to plug in a positive number. That's the first thing. But now, what's the deal about this plus and minus? The plus and minus is based upon where is theta over 2. Sine of theta over 2 is plus or minus this. I want to go figure out which quadrant theta over 2 is in. Because whichever quadrant theta over 2 is in, I say, well, what's the sine of an angle in that quadrant? And that's going to tell me whether I should use the plus or minus. So I need to know the quadrant of both theta and theta over 2. I need to know which quadrant these are both in. I need to know the quadrant of theta to do my calculation. I need to know the quadrant of theta over 2 to know which type of formula to use. So I've already determined that theta is in quadrant 1. How do I decide which quadrant theta 2 is in? What I'm going to do is I'm going to take this initial double-sided inequality. You notice in the middle here is theta. I want to convert that to theta over 2. How do we do that? Well, with an inequality, it's almost just like an equation. I can do whatever I want as long as I do the same thing to, in this case, all 3 parts of this. So since I want to know about theta over 2, you know what I'm going to do? I'm going to divide all 3 parts of this by 2. And then if I do my calculations here, I end up with a new inequality, except now it's an inequality for theta over 2. So initially, I had an inequality for theta, which told me theta is in quadrant 1. Now I've gone and figured out an inequality of theta over 2. Now theta over 2 is between 0 and 45. Where is that? That's also in quadrant 1. So now that I know theta over 2 is in quadrant 1, where is the sine of an angle in quadrant 1? What is it going to be? It's going to be positive. So I can sort of go here. The thing I like to do is just I sort of mark out the negative. I know my answer for the sine of theta over 2 has to be a positive number. So once again, when I have my formulas here, I have to decide up front whether the answer is going to be a positive or negative. And the way I determine that is I go figure out where is the angle theta over 2. And whatever quadrant it's in, that will determine whether my answer is plus or minus. So now, what they need to do, I know this is going to be a positive answer. Let's go figure out cosine of theta. Once I find cosine of theta, I can plug it in there and do the math. What was I given? I was given secant of theta equals 5/4. I don't like to work with secant, but I know I can switch secant to cosine by just taking the reciprocal. So you flip the fraction, and lo and behold, I've got what I need. I need to know cosine of theta. I know it's theta's in quadrant 1, so it's a positive 4/5. So I'm ready now to go ahead and plug it in. 1 minus, I did not rewrite the positive here because nothing's there, we know it's positive. 1 minus cosine of theta, 1 minus 4/5 over 2. Now I need to sort of simplify this fraction underneath the square root. First, 1 minus 4/5. 1 is the same thing as 5 over 5. So 5 over 5 minus 4 over 5 is 1/5. Now, when you have a fraction over a denominator, you can always, if you wanted to, you can always make that into a fraction and take the top times the reciprocal of the bottom. But one of the shortcuts is when you have a fraction over a denominator, this 2 ends up going into the bottom of your top fraction. So really, this is going to be square root of 1 over 10. Now here's where I'm not sure what WebAssign is going to want, because now I can take the square root of the top and the bottom separately. Square root of 1 is just 1. Now, I don't know if WebAssign wants this or if they want me to rationalize it. Sometimes they want me to get rid of the square root out of the bottom. I'm going to leave this for now. I hope I've done this correctly. And we go look at the answer. We'll see if this is the answer they want or if they wanted me to do something else. Let's go ahead and do the rest of them. Let's do the cosine of theta over 2. That formula says plus or minus square root of 1 plus cosine of theta over 2. And once again, before I even plug in the cosine of theta, I'm going to go determine, should this answer be positive or negative? Theta over 2 is in quadrant 1. The cosine of an angle in quadrant 1 is always positive. So once again, I can sort of mark out the negative. I know my answer is going to be a positive number. So I know cosine of theta is 4/5. So 1 plus 4/5 over 2. So 1 plus 4/5, 5 over 5 plus 4 over 5. It's like 9 over 5 over 2. So that's like 9/10. Square root of 9 is 3. So once again, I'm going to leave it like this, and we'll see if WebAssign is happy with that or if they want me to change it. Then the third one is the tangent of theta over 2. Here's the formula for that one. 1 minus cosine of theta over 1 plus cosine of theta. Once again, the first thing I want to do is I want to decide whether my final answer should be a positive or negative number. Tangent over theta over 2. What is tangent in the first quadrant? Theta over 2 is in the first quadrant. What is tangent in the first quadrant? It's positive. So therefore, I can mark out the negative. Now let's plug in cosine of theta. 1 minus 4/5 over 1 plus 4/5. So we've already, the numerator is 1/5. This is going to be 9/5. If you go ahead and simplify this complex fraction, take the top times reciprocal of the bottom, you actually end up with, now if I take the square root of the top and the bottom, I actually get 1/3. So I'm pretty sure that's going to be the answer WebAssign likes. Not so sure about the sine and the cosine. So hopefully I've done the math correctly. So let's see what WebAssign does. So once again, this is number 21. Oh, sorry, 22. Here it is. And they actually left it like I did. The sine is 1 over square root of 10. Cosine 3 over square root of 10. Tangent 1/3. All right, it's good to know. Now we're ready for 23. All right, Wow, only one problem with half angles. Now we're on to the last section. Looks like inverse trig functions. So let me write, it's like there's 3 parts, A, B, and C. I'll write each one of them down, and we'll talk about how do we determine inverse trig functions. So part A says, what's the inverse trig function of negative square root of 3 over 2? B says, what's the inverse cosine function of negative 1/2? And C says, what's the inverse tangent of negative square root of 3? And of course, they're asking for exact answers. So we're not going to use our calculator. All right, so let's talk about inverse trig functions. First of all, what I taught you, remind you of when you have an inverse trig function, you can think of this whole inverse trig function, this whole thing, you'll see me do this a lot, this whole thing is an angle. So let's just talk about part A. In my mind, here's the question I asked myself. For what angle, and in this case it's theta, is the sine equal to the square root of 3 over 2? So I'm basically saying, let me go find the angle where the sine is negative square root of 3 over 2. But, there's a big but. Whenever we're doing inverse trig functions, there's this limitation, there's this constraint. Now for sine and tangent, they limit where your answer can come from. They only allow your answer, you can only have angles in the first and fourth quadrant. I can't, my answer for an inverse trig function for sine or cosine, for sine or tangent, cannot be angles here in the third or fourth quadrant. That's just one of the rules for inverse trig functions. It has to do with the idea about inverse functions and one-to-one functions and a lot of sort of math definitions in theory. But for our purposes, all we know is that our answers have to come from over here. And the tricky thing is, when we think of the unit circle, we would think of this as 0. We would think of this as pi over 2. We would think of this as 3 pi over 2. But once again, for these inverse trig functions, they decide they don't want up here is fine, 0 and pi over 2, but they decided down here, instead of putting 3 pi over 2, they decide to think about this as a negative pi over 2, right? If you move clockwise around the unit circle, that's when you have negative angles. So bottom line is, when I'm looking for inverse trig functions of a sine or a tangent, my answer has to be somewhere between negative pi over 2 and pi over 2. So let's go back to our specific problem. I'm looking for the angle where the sine is negative square root of 3 over 2. I know that the sine is negative square root of 2 right down here. I used to call this 5 pi over 3, but in terms of this designation, this is actually going to be negative pi over 3. So you simply say the answer to part A, that's negative pi over 3. Let's go ahead and do part C, since I've got this drawn here. So part C says, let me go find an angle where the tangent is negative square root of 3. You got to remember, tangent's always a little bit of a pain. I always remember in my head, I think of it as sine and over cosine. So I'm going to go find an angle where if I put the sine over the cosine, it's going to equal negative square root of 3. First of all, the quadrant. For the tangent to be negative has to be quadrant 4. So my angle is going to be down here somewhere. Now you think about it, what fraction can I take to get a square root of 3? Well, that's where you're going to have the sine. You're going to want it to be square root of 3 over 2 and the cosine 1/2, right? There are those points where the sine is this, the cosine is this, because this thing equals square root of 3. Now it has to be negative, but we'll get that in a minute. So what's the angle where the sine is square root of 3 over 2 and the cosine is 1/2? Turns out it's this angle here. We used to call it 5 pi over 3, but for inverse trig functions, I'm going to call it negative pi over 3. So I'm actually at this same angle here because at negative pi over 3, the sine is negative square root of 3 over 2. The cosine's 1/2. When you divide them, you get negative square root of 3. So actually the answer for part C is the same as the answer for part A, negative pi over 3. B is the inverse cosine of negative 1/2. So once again, the question is, let's go find an angle where the cosine is negative 1/2. But the cosine is different than the sine of the tangent. For the cosine, it also has a limitation, but the cosine is like the top half of the unit circle. Now the nice thing is we start at 0 and we go to pi, so you don't have any negative angles. But whenever you do an inverse cosine function, your answer, your angle has to be between 0 and pi. It cannot be in the third or fourth quadrants. So therefore, I go back to my question. Let's go find an angle where the cosine is negative 1/2. Well, in terms of this top half of the unit circle, right here, 2 pi over 3 is where the cosine is negative 1/2. So for part B, you say, I guess call all of these theta. It's 2 pi over 3. So I'm saying part A is negative pi over 3. Negative pi over 3. B is 2 pi over 3, and C is negative pi over 3. So inverse trig functions are not really that hard. You just have to know that you have these constraints, these limits, these limitations of where your answer can be. So let's see if my answers are correct. This is number 23. So the sine, negative pi over 3, that's what I got. Cosine, 2 pi over 3. Tangent, negative pi over 3. So it looks like my answers are all correct. So on to 24. Once I turn off the key. So 24, now here's it. What's interesting is there are two different ways that they like to write inverse trig functions. The one we just did where you have a little -1 exponent, although it's not really an exponent. We should just call it a superscript. Superscript of -1. But then this problem, they have the thing, which I don't like to use it very much. I usually, a lot of times, don't even write it. A is what is the arc sine of 0. B is what is the arc cosine of -1. And C, what is the arc tangent of 0. So arc tangent is another way to write inverse trig functions. So here are those problems. Normally sometimes I'll even write this just because why do I want to have to think about two different things. Sometimes I'll just say, you know what, arc sine really means I can write it like that with my superscript of -1. And this is what I prefer, actually. Sometimes I get a problem like this. When I go write it down, I just automatically write it in this form. So I'll do that for all three of these, basically. So I'm looking for, once again, for 3 inverse trig functions. So now let's just see, there's not a lot of work to do. We just have to do a little bit of thinking. So this first one, once again, this whole thing is an angle. An inverse trig function ends up being an angle. So I'm looking for an angle where the sine is 0. So if we go back up here to our little diagram, my answer has to come from over here somewhere, where on the right hand side of the inner circle, what angle is the sine 0? It's right here, right? The sine is 0 at an angle of 0. Pretty straightforward. Cosine. I'm looking for an angle where when I take the cosine, I get -1. So here's my answers for cosine. Where along here, what's the angle where the cosine's -1? Well, it's right here. And what is that? That's pi. So the inverse cosine of -1 is pi. Inverse tangent. Once again, I'm looking up here, and I'm going to find an angle where the inverse tangent is 0, or where the sine over the cosine is 0. Well, that only occurs, so once again, this we have to think about it a little bit. For this whole thing to be 0, that only occurs when the sine is 0 and the cosine is whatever you want it to be. The key thing is what angle in here, what angle in here is the sine 0, which means the tangent is 0. And it actually occurs right here. At the angle of 0, the sine is 0. And so when you plug it in for tangent, it makes the tangent 0. So those hopefully are the correct answers. 0 and pi and 0. So number 24. Zero, pi, 0. Very good. All right. Hopefully not too bad so far. You're getting the hang of these inverse trig functions. Let's see what number 25 is. Looks like 3 more. All right. Maybe I'll try and work them on this same sheet of paper so I've got my diagrams handy. So 25A says, oh, I'm sorry, this is something different actually. Let's start a new piece of paper. We have to talk about this. These are not inverse trig functions by themselves. It's what they call composite functions. So let me write them down, and then we'll talk about how to think about these. So A says the inverse sine of the sine of 2 pi over 3. B, inverse cosine of 5 pi over 3 is what? And C is the inverse tangent of the tangent 7 pi over 6. So let's find the exact values. All right, so exact values. So these are called sort of like composite functions. So you have two things going on. You sort of got a trig function on the inside, but then you're taking the inverse trig function on the outside. And you always, if you need to think about it, you always work sort of from inside out. You can do the inside first, figure out what this equals, and then go here. Now, for these three problems, these are pretty easy to do because these are all special angles. Sometimes you may be given a problem where your original angle is not a special angle. So you think maybe you're sort of stuck. But actually, with these kinds of problems, you're not always stuck. Well, let's just go on and work through these problems. There is a shortcut you can use for these kinds of problems. So let me hold off on explaining the shortcut, and let's just think through these sort of logically because they're not that hard. So for instance, what this one says is, I'm going to start on the inside, and I ask myself, what is the sine of 2 pi over 3? Now this is just, for now, you can ignore anything about inverse trig functions. This is simply on the unit circle. Go find 2 pi over 3 and tell me what the sine is, all right? You've known this for weeks now. Sine of 2 pi over 3 is over there in the second quadrant, and I know it is square root of 3 over 2. So then it says, okay, this is square root of 3 over 2, and now I want to take the inverse trig function, inverse sine function of that, right? So basically, I just went ahead and I realized this is square root of 3 over 2. So I plug it in here. Now the problem becomes, what's the inverse sine of square root of 3 over 2? Now that we are taking an inverse trig function, we have to limit ourselves. In this case, since it's the sine, our answer has to come from the right-hand side of the unit circle. And even down here, we may have to write a negative angle. So ask ourselves the question, inverse trig function, this whole thing, an inverse trig function always ends up being an angle. So I'm looking for an angle where the sine is square root of 3 over 2. Where does that occur? It occurs right here. What is that? That's pi over 3. So the answer to this is pi over 3. Now some people might initially look at this and they might say an inverse sine function of a sine function, wouldn't the inverse and the regular one sort of cancel out? And wouldn't the answer be 2/3? So let me explain this real quick in case you're still confused by that. Here's the problem we were given. Some people think an inverse function of the normal function, these cancel out, and they just want to simply write in 2 pi over 3. In this case, it's not correct. Now, just to try and teach you what's going on, if this had been the original problem, and someone says, well, the inverse sine of the sine is pi over 3, that actually would be correct. So what's up? In this case, they don't cancel out. In this case, they do. And the whole key is, where does your angle start at? If the angle starts here on the right-hand side of the unit circle, then the little, I call this a shortcut, because a shortcut means I just look at this and I know the answer right away. If your initial angle is over here, then you can use your shortcut for the sine. If the initial angle is on the left-hand side of the unit circle, then you cannot use the shortcut. So where's 2 pi over 3? 2 pi over 3 is over here. Since it's not in the right-hand side, the shortcut doesn't work, and I have to figure this out. If my initial angle is in here, I can use a shortcut. My advice actually for the test, instead of trying to remember these shortcut rules, if you know the angle, I know 2 pi over 3, just do it. It's so simple. Just do it inside and then outside. Even if I was given this problem, what could I do? I could say, what's the sine of pi over 3? The sine of pi over 3 is square root of 3 over 2. So therefore, this becomes the inverse sine of square root of 3 over 2. Inverse sine has to be on the right-hand side. I know it's pi over 3, and there's my answer. Yes, I could have used a shortcut, but if you're going to try and use your shortcuts, you got to remember the rules for the shortcut. The shortcut doesn't always work. If possible, my advice is just do it the long way because it's not even that long. So the same thing for cosine. The shortcut for cosine means if the initial angle is in the top, then you can use your shortcut. So look at this one. 5 pi over 3. Where's 5 pi over 3? It's down here someplace. Turns out I cannot use the shortcut for this problem. However, I don't need to think about the shortcut. I can just do the problem, and I know I'm going to get the correct answer. Let's just do the problem. What's the cosine of 5 pi over 3? Cosine of 5 pi over 3, which is down here, is 1/2. So this problem now becomes the inverse cosine of 1/2. Now, since I'm doing an inverse cosine, I'm looking for the angle where the cosine is negative 1/2. My answer has to be in the top half of the unit circle. Where's the cosine 1/2? Right here. So the shortcut would not have worked because the answer is actually pi over 3. So now let's just go and do tangent 7 pi over 6. 7 pi over 6 is right here. Tangent is going to be the sine, which is negative 1/2 over the cosine, negative square root of 3 over 2. If you simplify this, you get 1 over square root of 3. So this problem now becomes the inverse tangent of 1 over square root of 3. So now I'm looking for an angle along the right-hand side here where the tangent is 1 over square root of 3. It's going to be in quadrant 1 because tangent's positive. As it turns out, if you look at your sines and cosines, it's going to be this one right here, which is pi over 6. So it should be pi over 3, pi over 3, pi over 6. Pi over 3, pi over 3, pi over 6. Very good. All right, now we're on to problem 26. So I have like maybe 4 problems left. Oops, let me turn off the key. All right, looks like 3 more. Actually, these problems are different because on the last problems, I can show you, these 3 started out with inside were just normal trig functions, and then you took the inverse trig functions. This one, the inside are the inverse trig functions, and then you take trig functions. Interesting. So let's write these down and work through those. Although actually, they're not going to be that hard because we're going to use the same method we used a minute ago. We're just going to work from the inside out. So this first one is the sine of the inverse cosine, negative square root of 3 over 2. B is the cosine of the inverse tangent square root of 3. And C is the tangent of the inverse sine of -1. Now, one other difference I noticed real quick before we switch back is the previous question, you notice it was sine, sine, cosine, cosine, tangent, tangent. That's why I talked about those shortcut rules. Here, it's actually the sine and the inverse cosine. Cosine of inverse tangent, tangent of inverse sine. They're not even the same two types of trig functions here. So there's definitely no kinds of shortcut rules. Here we just have to, we're going to start from the inside, figure out the inside, and work from the inside out. So here we are. So these are not that hard. First thing I notice is the inside. This is an inverse cosine. It's an inverse trig function. I tell myself, just to keep from getting confused, that whole thing is going to be an angle. Now I'm going to go figure out what that angle is. Then I'm going to plug it in here. Inverse cosine function, -3, negative square root of 3 over 2. Basically, I'm saying, okay, let's go find an angle where the cosine is the negative square root of 3 over 2. And the answer has to be in the top half unit circle. So where on here, where's an angle where the cosine is negative square root of 3 over 2? You know what? It's right there, 5 pi over 6. So this inverse cosine function is actually 5 pi over 6. So I replace this inside with that, and now it's saying take the sine. So this whole thing is 5 pi over 6. I replace this whole inverse cosine function with 5 pi over 6. So now the problem becomes, what's the sine of 5 pi over 6? Once again, at this point, nothing to do with inverse trig functions. It's just the normal sine. You say, what's the sine of 5 pi over 6? 5 pi over 6 is right here. What's the sine? One half. B, inside. Once again, this is going to be an angle. Inverse tangent of square root of 3. So I'm asking myself, let's go find an angle where the tangent is square root of 3. But since it's an inverse tangent function, the angle has to be here on the right-hand side. So once again, since it's tangent, it's going to be an angle where the sine is square root of 3 over 2 and the cosine is 1/2 and it's positive. It's got to be a quadrant 1. Where does that occur? Occurs up here at pi over 3. So the inverse tangent of square root of 3 is pi over 3. So I replace this whole inverse tangent function with pi over 3. And you end up, the problem now becomes, what's the cosine of pi over 3? Pretty straightforward, right? Pi over 3 is right here. What's the cosine? 1/2. All right, not too bad. This last one, the inside, the inverse sine of -1. Once again, this whole thing is going to be an angle. It's an inverse sine function. I'm looking for an angle on the right-hand side here, an angle where the sine is -1. Where's the sine -1? It's down here. What is this down here? Don't say 3 pi over 2. For an inverse sine function, it's actually negative pi over 2. When we're in the bottom, we want to use negative angles. So for this problem, this inverse sine, I can replace with negative pi over 2. So this problem becomes, what's the tangent of negative pi over 2? So you think of your unit circle, where's negative pi over 2? It's down here. What's the tangent? Tangent sine over cosine, right? So it's really sine of negative pi over 2 over cosine negative pi over 2. What's the sine of negative pi over 2? It's negative 1. What's the cosine of negative pi over 2? What's the cosine down here? It's actually 0. What is it when you have a number divided by 0? It's actually undefined. And I think in WebAssign, they actually want you to type in the word undefined. So I think my answers are 1/2, and undefined. But we'll see if I'm correct. Problem 26. One half, undefined. Nice. All right. What's the 3 more problems? 27, 28, 29. We'll see what they are. 27. Looks like 3 more of these. All right. No complaints. Hopefully we can figure these out. I'm gonna write them down. Look at them, talk about them. So 27A, the sine of the inverse tangent of negative square root of 3. B is the cosine of the inverse sine of 1. And C is the tangent of the inverse cosine of 0. As usual, find exact values and such. All right, I got myself a little bit of room. All right, so we've done this before. Let's see. Inside is an inverse tangent function. Right away, I always just like to tell myself this whole thing is an angle. Let's find out what angle it is. So once again, inverse tangent, I'm looking for the angle over here on the right-hand side where the tangent is negative square root of 3. So I know it's going to be in the 4th quadrant. And by now, hopefully you realize square root of 3 is going to be the one where the sine is square root of 3 over 2 and the cosine is 1/2. That's going to be down here. But once again, we're going to call that negative pi over 3. So this is really the sine of negative pi over 3. So what's the sine of negative pi over 3? Negative square root of 3 over 2. I hope, unless I made some mistake. Problem B. Inside is an inverse trig function. This inverse trig function is going to be an angle. So I'm now looking for the angle where the sine is 1. Since it's an inverse sine function, it's got to be on the right-hand side. So where is the sine 1? Well, up here at pi over 2, right? So this now becomes the cosine of pi over 2. What's the cosine of pi over 2? 0. Not too bad. Almost seems too easy. Here, the inside is the inverse cosine of 0. This is going to be an angle. So now, inverse cosine, my answer has to be in the top of the circle. I'm looking for an angle where the cosine is 0. That happens up here, right? At pi over 2. So the inverse cosine of 0 is pi over 2, so this becomes the tangent of pi over 2. Now the tangent of pi over 2 is like sine over cosine. Sine of pi over 2 is 1. Cosine is 0. We're back again with 1 over 0. Looks to me like part C should be undefined. So negative square root of 3 over 2, 0, and undefined. We shall see. X square root of 3 over 2, 0, undefined. Yep. All right. Couple more left. Ready for 28. All right, see 28 here? Now we're going back to arc sine, arc cosine. When I write these problems down, I'm not even going to write arc sine, arc cosine. I'm going to write the notation I'm used to. So let me write these down, and then we'll talk about what's going on. So 28. Actually, let's do them one at a time, because these actually are sort of involved problems. Let's just do part A and talk about it. The sine of the inverse sine of square root of 2 over 2 plus the inverse cosine of 0. Although this first one actually isn't bad. The other two are going to be more work, but you'll see why. All right, let's talk about this. So what I've got now is the whole key to this is, let's look what I've got here. I'm taking the sine, and inside the parentheses, I'm actually adding together two inverse trig functions. Now the key to this problem, which this one's going to be pretty easy to solve, the next two are going to be more difficult. First thing I realize, anytime I have an inverse trig function, it always equals an angle. So the first question I ask myself is, well, do I know what this angle is? Can I figure out what is the inverse sine of square root of 2 over 2? And actually I can, because this angle is actually going to be a special angle. Because basically I ask myself, what's the angle where the sine is square root of 2 over 2? Now for inverse sine, it's got to be here, but I know that right here, the sine of pi over 4 square root of 2 over 2. This actually equals pi over 4. And then I say, how about this inverse trig function? Inverse cosine of 0. I need to go find an angle where the cosine is 0. And it has to be in the top. Where does that occur? Right here, pi over 2. So really, what I have now is pi over 4 plus pi over 2. And when you add those together, pi over 2 plus pi over 4, if you get a common denominator, this would be 2 pi over 4. It's actually sine of 3 pi over 4. And what's the sine of 3 pi over 4? It's right there. Square root of 2 over 2. I'm going to check this answer, and then we're going to start part B, and I'm going to explain to you why part B is a lot more work than part A. So let's just go make sure I didn't mess up. So 28A. Now square root of 2 over 2 is the same thing as 1 over square root of 2. So our answer is correct. Now let me go write down part B, and we'll talk about it, and we'll start working it out. I'm going to explain to you why part B is a lot harder than part A. So part B says the cosine, once again, I'm not going to write arctangent, I'm just going to write inverse tangent of -4/3 minus inverse sine of 3/5. All right, let's talk about this. Part A and part B are alike in that part A, I'm taking the sine on the outside, and here it's cosine. And then inside in part A, I have two inverse trig functions, which I'm adding together. I'm doing the same thing in B. I'm also adding two inverse trig functions. But the big difference is, when I looked at part A, and I tried to look at these inverse trig functions, these were special angles. I was right away able to look at the inverse sine of square root 2 over 2 and say that is the angle pi over 4. And when I looked at the inverse cosine of 0, I right away said that's pi over 2. And I was able to plug those in here and then finish the problem. You know what's going on in part B? This is not a special angle. I don't know what the inverse tangent of -4/3 is. I don't know what the inverse tangent of 3/5. I know it's an angle, but you know what? It's not a special angle. I can't just plug in an angle from looking at the unit circle that works for these. So what do we do? Well, let me actually rewrite this problem on a new sheet of paper because it's going to take a fair amount of work to figure this out. So let me rewrite it. The cosine of the inverse tangent of -4/3 minus the inverse sine of 3/5. Here's what I'm going to do. I know this is a trig function. I'm going to call it θ1. That little 1. I write that there because this is also an angle, which I'll call θ2. So that's a way to, this problem actually deals with two angles, two different angles, so I'm going to keep them separate like this. So really, if I wanted to, I could rewrite this problem as the cosine of θ1 minus θ2. Now, I don't know what θ1 and θ2 are, but it's interesting. For now, I'm going to rename these inverse trig functions and just give them the name of an angle, because I know they are angles. I don't know what they are, but I know they're angles. I'm going to go ahead and say, you know what? I can go back to a couple sections ago, and this is, I can use the formula for the cosine of the difference of two angles. Remember my old sheet here? Cosine of u minus v. I'm actually going to use that formula here. And it says the cosine of θ1 times the cosine of θ2 plus the sine of θ1 sine of θ2. So basically, if I can figure out cosine and sines of θ1 and θ2, then I can plug them in and I can actually solve this whole problem. But I really don't know what these angles are. Now let me explain this to you, and hopefully this will become clear. Let's look at this first one. Here's what they've given me. inverse tangent negative 4/3. And I said, I know this whole thing is theta 1. Now, when I've been doing these inverse trig functions, you know what I've been saying. I look at this and I say, I need to go find an angle where the tangent is negative 4/3. Now, what I just said, I could actually write it down to make it even more clear. I'm looking for an angle where the tangent of that angle is negative 4/3. If I want to write down what I just said, here's basically what I'm saying, right? When I look at an inverse trig function, I ask myself the question, I need to find an angle where the tangent is negative 4/3. That's what this is. This is an angle where the tangent is negative 4/3. When you think about it like this, and I want to learn about this theta 1, like I want to learn what I really need up here. I need the cosine and sine of theta 1. What did we do many times a while ago? If I know a trig function of an angle, I would create a right triangle. Tangent is negative 4/3. I don't care about the negative right now. All I care about is the 4/3. TOA, opposite over adjacent. So let's take a step back. What have we done? We've taken our first inverse trig function. I asked the question to find the angle of this inverse trig function, and I decided to go and rewrite it like this, because this inverse trig function is really saying the same thing as this right here. If I solve this and solve this, I'm asking myself the same question. And I know how to solve this kind of problem. I create a right triangle. I should call this theta 1. Now, the very tricky thing is, I know, because the origins of this was an inverse trig function, I know all along this has to be in quadrant 3. So when I go get my functions here, I know I'm in quadrant 3. Because an inverse trig function has to be in quadrant 3. So this gives me a way now, when I go to my formula here, when I'm looking up cosine of theta 1, I go to this triangle. This is like a theta 1 triangle. And I can say the cosine, ca, is adjacent over hypotenuse. And then I have to decide whether it's a plus or minus. I misspoke here. Hopefully you guys didn't get too mad at me. Actually, when the tangent's negative, I have to be in quadrant 4. Because the inverse tangent is either quadrant 1 or quadrant 4. Sorry about that. But now what I'm going to do is I'm going to take my other theta 2. I'm going to do the same thing. I'm going to take this inverse trig function. So here it is. To solve this, normally I ask myself, let's go find an angle, theta 2, where the sine is 3/5. Another way of writing that is, I'm going to go find an angle, theta over 2, where the sine is 3/5. This and this, I'm saying the same thing. But hopefully it's clear when I see it like this, that I can go and create a right triangle for theta 2, sine, opposite, hypotenuse. And now it's almost like this is a right triangle for theta 1, and it's in quadrant 4. This is a right triangle for theta 2, and because the inverse sine is positive, this is in quadrant 1. Now, based upon these two triangles, I can figure out my cosines and sines and actually solve this problem. So let's do that. Cosine of theta 1. I go to my theta 1 triangle and I say, what's the cosine? So ca, adjacent or hypotenuse, 3/5. And I'm in quadrant 4. Cosine is positive in quadrant 4. I just write 3/5 times the cosine of theta 2. I go to my theta 2 right triangle. I say, what's the cosine? So ca 4/5. In quadrant 1, cosine is still positive. So there's cosine of 1 times cosine of theta 2. Cosine of theta 1 times cosine of theta 2. Now I say plus sine of theta 1. I go back to my theta 1 triangle, say, what's the sine? Sine is opposite over hypotenuse. But since it's the sine and I'm in quadrant 4, I know that's going to be a negative number. So it's actually negative 4/5. Sine of theta 1 times sine of theta 2. For the sine of theta 2, I go to my theta 2 triangle and I say the sine is the opposite over hypotenuse, and in quadrant 1, it's a positive number. So it's times 3/5. That was a lot of work. Let's go and finish this, and then we'll summarize what we actually did. 12/25 minus 12/25. Amazing enough, you do all that work, it equals 0. Let's review what we did. I told you part B was a lot harder than part A. And the reason it's harder is because I don't know. Look at these two inverse trig functions, inverse tangent, inverse cosine. When I look at the numbers inside, these are not special angles. I don't know what these angles are. What I did though, I called the first inverse trig function, I just call it theta 1 just to make it simpler, and this one theta 2. So I really have is cosine of theta 1 minus, I really have the cosine, the difference of these two angles. And I used my formula for the cosine difference of angles, and I got this formula. So now I said, if I can figure out what cosine and sine of theta 1 are, and cosine and sine of theta 2, I could plug them in. But how do I figure out trig functions of theta 1 and theta 2? Well, I took this initial information and thought about it, and for theta 1, I was able to create a right triangle, and for theta 2, I was able to create a right triangle. And once I have the right triangles, then I was able to figure out my sines and cosines. So it's a pretty involved problem. Now let me check and make sure I got it correct. The answer should be 0. That may be about the hardest problem we've done so far on these practice problems. So that's 28B. And the answer is 0. So now, unfortunately, I think part C is going to be like part B. I'm going to have to jump through all the hoops. So let's do it. Maybe by now. I better start with a clean sheet of paper. It's a lot of work. Although now that we've done it once before, it shouldn't take as long. So C, once again, I'm not going to write any arc stuff. I'm going to write tangent of the inverse tangent of 1/3 plus the inverse cosine of 7/25. So I think we're going to do the same kind of thing we just did. So I'm taking the tangent, but inside I'm adding two inverse trig functions together. Now an inverse trig function I know is going to be an angle. I'll call this theta 1, and this I'll call theta 2. So let's look at the last time. Let's go ahead and rewrite this. What I really have is theta 1 plus theta 2. And I'm going to right now just going to go to my formula sheet and see. Here's the equation for the adding the tangent of two angles added together. And it's going to be tangent of theta 1 plus tangent of theta 2 all over 1 minus tangent of theta 1 times tangent of theta 2. Pretty messy formula. So what I really need to be able to solve this problem is figure out the tangents of theta 1 and theta 2. I don't know those because those aren't special angles. So what I'm going to do is I'm going to take and create a right triangle for theta 1, theta 2. So what this is really saying is I'm looking for the angle theta 1 where I take the tangent and it equals 1/3. Since the tangent's positive, I know this is a quadrant 1 angle. So here's theta 1. Tangent is opposite over adjacent. Hypotenuse is going to be 1 squared plus 3 squared. Looks like square root of 10. For theta 2, I'm going to do the same thing. Another way of saying this is the cosine of this angle theta 2. I'm looking for an angle where the cosine is 7/25. This is also in quadrant 1. So I can create another right triangle. So this is for theta 2. So ka, adjacent over hypotenuse. Now this leg is going to be 25 squared minus 7 squared. I hope that's a nice number. Actually, I have to grab my calculator. 25 squared minus 7 squared, which is 49. It is, thankfully. So now, actually, you know what? I don't even need to make this right triangle because I need the tangent. I already got the tangent. So actually, maybe some of you realize that I don't need this. I needed to create this right triangle because I need the tangent. Matter of fact, I'll just write it here. What's the tangent for this one? The tangent of theta over 2 is TOA, opposite over adjacent. So basically, here are the two numbers I need to now finish my problem. So I'm going to write it down here. So tangent theta 1 plus theta 2. Tangent of theta 1 is 1/3 plus tangent of theta 2, 24/7 over 1 minus tangent of theta 1, 1/3 times tangent of theta 2, 24/7. Now this becomes a pretty ugly fraction to figure out. Need to combine these two fractions at the top. Looks like the common denominator is going to be 21. Let's not skip any steps. When I get a common denominator, let's multiply by 3/3, so it's 60, like 72/21. Now this is 1 minus 24/21. So if I want to, I can say this is 20/21. So now the top is going to be 79/21 over minus 3/21. 79/21 times minus 21/3. 21's cancel out. Now we can cross our fingers and see if that's the correct answer. Minus 79/3. Amazingly enough. Oh, forgot to throw in the key. Oh, actually it's correct. All right, it's a relief. All right, last problem. So those last two parts were pretty involved. We'll see what 29 is. All right. Looks sort of interesting. Maybe we'll just do one of these at a time. So this first one, 29a, is the sine of 2 times the arc cosine, which I'm going to write as inverse cosine of -7/25. Once again, exact value, always. The key to these problems like this, so once again, inside here, I've got an inverse cosine function, although I've got also multiplied by 2, which is a new twist, all that stuff inside of the sine. You always work from the inside out, and the first thing I realize is this is an inverse cosine function, which ends up being an angle. So really, if I write this a little simpler, this really ends up being a problem. If this whole inverse cosine is an angle, this really is a problem of, I can write it as sine 2 theta. And actually, I know the formula. There's a formula. This is like a double angle. Sine of 2 theta is 2 sine theta cosine theta. So let's start with the last problem. If I can learn what the trig functions are for this theta, then I can solve this. What do I know about theta? Theta is the inverse cosine of -7/25. Once again, if I ask myself the question, I'm saying I need to go find an angle where the cosine is -7/25. Another way of writing that is, here's an angle where the cosine is -7/25. Since the cosine is negative and it's an inverse cosine, that's where this started out. I know this has to be in quadrant 2. So I'm going to go ahead, I can create my right triangle. So ka, I don't care about the negative, but ka is adjacent over hypotenuse. I think we just did a 25 and a 7. We did, and this ends up being 24. So now, quadrant 2, I can say 2 times the sine of theta. This is the triangle for theta. Sine is opposite hypotenuse. And in the second quadrant, the sine is positive. Cosine's right here, -7/25. And now 2 times 24, wow, 48 times -7 over, I think 25 squared is 625, but I need to get my calculator to finish this problem. Let me confirm, 25 squared, yep. And 48 times 7, if I do it in my head, just for practice, although I'm going to check it, should be 280 plus 56. 280 plus 56 is 3. Is that right? It's always good to. Yep. Now the question, does this reduce? It may not. I guess I'll go look at WebAssign and see. It's not obvious to me how it reduces. So 29a. Wow, it's correct. Negative 336 over negative 625, amazingly enough. All right, let's write down B and C maybe at the same time, see if we can figure them out. Maybe I'll do B on this sheet of paper and then write C down on the next one. So this is the cosine of 2 times the inverse sine of 8 over 17. Just to save time, then write down the third part C. Tangent of 2 times the inverse tangent of 5 over 4. All right. Last two problems. I think the same idea here. Inside here is an inverse sine function. I know an inverse trig function is always an angle. So I could rewrite this as cosine of 2 theta. And double angle formulas, that's where I have 3 choices. I wonder if it matters which one I choose. You know what? Aha, it does. One of them's going to make it easier. How about using this one? So once again, here's what I'm saying. For the cosine to the double angle for the cosine, I have 3 choices here. I'm going to choose this middle one, and you're going to see why in a minute. Look at the top one has cosine and sine. The middle one has only sine. The third one has only cosine. I'm going to choose the one that I think is going to be easiest. I think it's going to be the middle one. Now, let's see if I'm correct. So cosine of 2 theta, I'm going to use 1 minus 2 sine squared of theta. So if I can figure out the sine of theta, then I pretty much can plug it in there and solve this problem. What am I given about theta? Theta is the inverse sine of 8/17. So basically, you know what this is saying? This is saying I need to find an angle where the sine is 8 over 17. Another way of saying that is the angle theta has to be 8 over 17. I have now found the sine of theta. I found what I've needed. So I can just plug it in here, right? 8 over 17 squared. I don't even have to build a right triangle or anything. 1 minus 2 times 64. I don't know what 17 squared is. 17 squared is 289. So 1 minus 128 over 289. 289 over 289 minus 128 over 289. I think it should be 161. I better make sure. Minus 128. Yep, 161. And I don't think that reduces. So in a minute, we'll check, see if that's correct. That's part B. So let's finish part C. See if we can go out with a bang. What is this one? Tangent 2 times inverse tangent of 5/4. Well, by now, hopefully we all know the inverse trig function is an angle. So this is really tangent of 2 theta. My formula for 2 theta, I don't have a choice, there's only one, is 2 tangent of theta over 1 minus tangent squared of theta. However, this is not going to be too bad because when I go try and figure out theta, basically I can say tangent of theta equals 5/4, right? Because an inverse trig function, I say, I need to go find what's the angle where the tangent is 5/4. That's what this says. This is the angle where the tangent is 5/4. So tangent of theta is 5/4. So now I can just plug in 2 times 5/4, 1 minus 5/4 squared. So 10/4, 1 minus 25/16. I'll call that 5/2 over, this is 16/16. So it's minus 9/16. 5/2 times minus 16/9. 50, that gets negative 80/18. I can divide it by 2, 40/9. So here are parts B and C, some pretty ugly fractions. 161/289 and negative 40/9. So we'll cross our fingers and see if I did these correctly. (161/289) and minus 40/9. Wow, it's a good day. All right, so that's the end of the practice problems for test number 3. So hopefully, as you work through these, if you need help, you can look at these videos and understand what you're doing. So let me stop this.